Hey, let's say you have a biscuit on a plate. Looks tasty, right? But what if I break it? Nothing, it just breaks. But what if it joins back? And then breaks again. And then yet joins back. And still breaks. And keeps on doing this forever. It would be strange, right? This is what physicists would call a time crystal. Hi, this is Sarabjit, an integrated PhD student from JNCSR, and today we're going to talk about time crystals. So yeah, I know it sounds a lot like Thanos' time stones, which he used to snap half of the universe into dust. But trust me, time crystals are even more interesting. So what are crystals in the first place? So you see, crystals are atoms which are arranged in a periodic fashion. So you have atoms which are arranged periodically in one dimension along the x-axis, you have a 1D crystal. If you have atoms which are arranged periodically in 2 dimensions, you have a 2D crystal. And if you have atoms arranged periodically in 3 dimensions, you have a 3D crystal. But wait, is that all the dimensions that we have got? The answer is no. We have time as the 4th dimension. So what if you can have this periodic arrangement in the 4th dimension too, that is the time dimension? Then what you get is basically a time crystal. Let us understand it in a more intuitive manner. Let's say you have gas molecules in a box. If you move any distance from the corner, you get a gas molecule because they are in random motion. So the distance you have to move from the corner to get a gas molecule can be any length. So that's why gas molecules have something that we call continuous space translational symmetry, which is just a fancy name that you do any continuous movement and you will get a gas molecule. But let's say you have a solid like this 2-dimensional crystal. To get an atom, you have to move some specific distances. If you move some arbitrary distance, you won't get an atom. Specifically, you have to move distances which are integer multiples of the atomic separation. And that's why people say solids have discrete space translational symmetry, which is just a fancy name to say that you need to move some discrete set of displacements in order to get atoms. So there is a break in symmetry when you move from gas to a solid. However, both of these states of matter preserve something called continuous time translational symmetry. So this is the picture of the solid at any time, and you can see that it looks the same. The solid looks exactly how it is today, as it was yesterday, and how it will be tomorrow. And that's why matter have continuous time translational symmetry. Now let's consider a solid in this format. Let's say at time equal to 0, it has a configuration with atomic separation being A. At time equal to small t, it has a different configuration with atomic separation B. And at time 2t, it has again the similar configuration with atomic separation A. Which means at every 2t intervals, it gives you back the same atomic configuration. This means that it is periodic now, but in time, it has discrete time translational symmetry. This is what is called a discrete time crystal. And if you look at it over a long time, you will find that it oscillates like this. This is analogous to a swing, where the swinger achieves some fixed positions after regular time intervals. But a swinger needs a push from the pusher. Do time crystals too need pushes? Of course it does, because if it didn't, then you would have something called a perpetual machine. That is, the oscillators would oscillate even without some input energy. That is, you have output without input, which is not possible. So you'll be wondering, then what's the hype about time crystals? They are just swings on an atomic level. But that's not the case. You see, the frequency with which a swing moves is the frequency with which the pusher pushes it. But that is not the case for time crystals. You give some push, but the time crystals oscillate with some other frequency. They're like, thank you for the push, but then we are going to oscillate in whatever manner we want to. It turns out that these oscillations are completely a result of atomic interactions. In these time crystals, this oscillatory motion is the state of lowest energy, which is just a fancy word to say that when these atoms are oscillating in a time crystals, they are more stable. So you cannot extract any energy further, which prevents you from making a perpetual motion. These time crystals can be used to make something called quantum computers, which are like normal computers but million times faster with high efficient computing powers, which means that they're going to make our lives easier, and that's why they matter. But then the crucial question is, what are these kind of interactions which give rise to this oscillatory motion? Well, that is a mystery which we all intend to find out.